Okay, thank you. So now you have some notes, but as I said yesterday, it's a draft, it's not final. And in particular, if you look at my home page address, it's not the good one. The good one is here. Okay, anyway, you find my, okay, you Google my name, but don't confuse because there is another Pierre Schapira who is a politician, a French politician, and not exactly kind of person that I like. Yeah, but I'm not. So don't confuse. But if you type Pierre Schapira math, then there is only one until now. And for those, I know there are people here who know everything, and other people who don't know so much. In my notes, honestly, there are good courses. And if you want to learn sheaves, homological algebra, D modules, so you look at lecture notes in my home page. And then there are lecture notes more or less elementary, and other one which are called M1, M2, that's Master 1, Master 2 in France. And here you can, especially there is one which is called Algebra and Topology, which is rather elementary, but I think it's good introduction to sheaf theory for those who don't know homological algebra and sheaves. Okay, and there are notes on D module, on the half category, many things. Okay, and there is another section which is called conference. And then in a few days, I will add, I will correct my notes and put them in this section, conference. Okay, but I think my notes are not almost good until the last section, which I had no time to read again. Okay, so today it's very ambitious. I want to explain a proof, sketch of proof of the Riemann-Hilbert so-called Riemann-Hilbert correspondence, but in the regular case. There is a new paper by Schapira and D'Agnolo for the irregular case, but it's very, very complicated. And I'm not sure it's final. It's too complicated. But this one now, I think, now we understand the things. So it's a correspondence between regular holonomic D modules and constructible sheaves. I will state it clearly later. And so in my talk, first, I need some compliments on D module. There are 3 parts, more or less. And I introduce something which is interesting in itself. It's the subanalytic topology. And after, the proof of the theorem. So the subanalytic topology, as we will see, it's in the sense of Grothendieck topology, of course. It's not classical topology. And okay, let me recall me to explain the history of the Riemann-Hilbert correspondence, which is a little controversy. Okay, so let's come back to. So now I'm sorry for those for specialists, but I will be very elementary. I recall a few basic things on D module. Okay, so X is a complex manifold, or maybe it's better to call it X with a structure sheaf, OX, a complex manifold, analytic. I'm not algebraic. On dx, we have seen it 2 days ago, the sheaf of holomorphic differential operators, and we have seen that it is right and left coherent. In fact, in the analytic case, there is something better than coherent. It's called Noetherian as a sheaf. So we have the derived category, bounded derived category of coherent D module. So when I write D module, I mean left, but there is an equivalence between left and right. So when you have a ring, non-commutative ring, if I is a ring, A up is the same ring, but the product is inverted. Okay, here the product is A B, and here the product is B A. Okay, so left A module are the same as or right A module are the same as left A up module. And this equivalence is given, even not coherent, to M. You associate omega X tensor, maybe. Omega X is a shift of the differential form of maximal degree. In this sense, and in the other sense, and you associate, this is the line bundle, so you can take the inverse like that. Okay, so you just have to remember that we have not to worry between right and left, it's almost the same thing. Okay, we have to make the distinction, if you, but it's not important. Okay, so now I want to describe a few operations on D module. So first, internal operation and external operation. So there is a duality, or two dualities, no, let's say only one. The dual from dB dx to dB dx. So it's not like that. It's open. It's a contravariant functor. Don't confuse the opposite category and the category and the opposite ring. Huh? It has nothing to do, of course. Okay, this is the opposite category. So to M, you associate R om over D. M. So if I write dx, if I do that, I will find a right D module because M is left, and it will be right. So I have to. So I look at my notes, and there is a shift also. So to remain in the right D module, I take this and I take a shift so that the dual of OX will be OX, for example. Otherwise, it shifts, okay? What does it mean? Maybe I give an example. If you take D, this D module, P, no, okay, no, I don't give examples. It's not so interesting. Okay, so there is a duality functor. And that another, so there are many functors, we shall see. There is another internal tensor product, but it will come later. So maybe there is a, from, yeah, what I should have said here, which is obvious, it goes from coherent to coherent. And if M is coherent, then the dual of M is canonically isomorphic to M. It's an auto-anti-equivalence for coherent D module. Like for a vector space, if a vector space is finite dimensional, it's isomorphic to its bidual. Okay, so there is another important functor, which is a functor of solution, which goes to sheaves. So to M, you associate the complex of holomorphic solution So here maybe I will explain, because for those who are not used with Rm, for example, assume that M is quasi-isomorphic to some complex, bounded, free complex. So this is quasi-isomorphic to M, which means that you have a, if I put M here, it means that I have an exact sequence, okay? So in this case, this complex will be, so here you have P0 acting on the right, then you will have OX power N0, P0 acting on the left, OX power N1, OX power NM0. Okay. Yeah, of course. P0 is a matrices of differential operators. So it goes from dx n1. It's linear algebra over a ring, over a sheaf of ring. Okay, and there is another functor very similar, which is called the Durham functor, dB dx to dB cx. It's almost the same to M to associate the differential form, which is a right D module M. Okay. On these two functors, if M is coherent, then the solution functor is the same as the Durham functor applied to the dual of M up to a shift. Okay. So you see Durham or Sol play the same role. We are not to worry about that, but they are basic. And as I recall, what I said in my first talk, that the macro support of so if M is coherent, the macro support of the complex of solution is equal to the characteristic variety of M. And of course, you can put Durham instead of Sol, because the characteristic variety of the dual is the same as the characteristic of the module. Okay? Car M equal car dm. Okay. So that's some basic notion. And now I need, for what I want to do, external operations. So now I have a D module on X and another D module on another manifold Y. Then I can define the external product. So if I take the external product as a sheaf, it will be a dx. This thing is a dx external product dy module, but I want a dx cross y. This is different because I am analytic and not algebraic. If I take OX external with OY, it's contained, but it is different of OX cross y. Because, of course, for polynomial it's true, but not for analytic function. An analytic function of two variables is not the tensor product of an analytic function in X and an analytic function in Y. So I have to complete by dx cross y tensor over dx external dy of this. Okay, that's the external product. And the characteristic variety of the external product, in case they are coherent, is the product of the characteristic variety. Okay, that's easy. So now assume I have a morphism from F, holomorphic map, from X to Y, and I want to define direct image or inverse image of D module. Then it's a little more difficult. There is a bimodule, dx to y, a dx f minus 1 dy by module. So it means that it's dx module on the left, f minus 1 dy on the right. Okay, left action, right action. So what is dx to y? As a sheaf, so here it's easy. So this is true as a OX f minus 1 dy module, but not as a dx module. The action of dx here is not the stupid action on OX. So I just say quickly, maybe it's useless because it will need more details. I have, if V is a vector field on X, I can take its image. So maybe I have Tx, x cross y, Ty by f prime. So the direct image of V can be written as a finite sum, Aj tensor Wj, where Aj is in OX, Wj is a vector field in Y, or in f minus 1 is here. Okay, so you define the action. So the action of vector fields theta x on OX tensor f minus 1 OY dy is given by V applied to A tensor P. Okay, so A P will be given by V of A tensor P plus sigma J A J double tensor. It's a little complicated. WJ composed with P. Anyway, there exists a formula. Okay, so you can forget this for a while and just remember the following. The important thing is that you have this bimodule. Okay, so what is important is the following. You have f from x to y. So you have dx to y, which is a dx f minus 1 dy by module. Okay, so with that, now we can make inverse image and direct image. So, for example, if M is a a right dx module, we can define the direct image of M. So d f star, I use Schapira's notation. That means the direct image in the category of d modules. So it will be the direct image as a sheaf of M tensor over d dx to y. Okay. So you see this is a f minus 1 dy module. You take the direct image, it will be a dy module. Okay. So it's easier with right because you know direct image means more or less integration. And when you integrate differential forms. That is, in the language of d module, it's right d module. The inverse image now is for left dy module. So d f minus 1n will be dx to y tensor f minus 1 dy f minus 1 n. And everything is derived, of course. Okay. So the inverse image is easier because there is one derived functor left. But the direct image is very complicated because you have a right derived functor and a left derived functor. Okay. Okay, so there is a whole theory of these things. Okay, this is a definition, but there is a lot to say, enormous to say. In particular, it's interesting to know what happens with coherent D module and where is the characteristic variety and so on. So I will be very sketchy. I will just give. So maybe there is something to say which is important. These operations are functorial. Because if you compose dx to y tensor, so this with f minus 1 dy, f minus 1 dy to z, this is dx to z. So the operations are functorial. Okay. So okay. So in particular, you find that the direct image d g star d f star m is isomorphic to d g composed with f star m. And similarly for the inverse. Okay, so these are functorial. So in practice, it's very useful because when you have a morphism from x to y, you can decompose it by the graph and project. So any morphism is decomposed in a closed embedding on the projection. And in practice, it's very useful, of course. Okay, I cannot make a whole course on D module now. I just explain the main result that I need. So the first theorem is Cauchy-Kovalevsky Kashiwara, because it's Cauchy-Kovalevsky extended to D module, and it is in Kashiwara's thesis in 70. So at this time it was absolutely, of course, also Sato has some role in this. Because at this time, until now, to be honest, people working on PDE are unable to work with systems. They work with one equation with one unknown, or sometimes a square matrix. Okay? But over-determinate system is seems out of reach. But the language of D module says that. So what does it say? You have f from x to y. So on n, a coherent dy module, and assume f is non-characteristic. with respect to n. So it's exactly the same definition as for sheaves. And in fact, the definition for sheaves was inspired by the definition for D module. It means that Fd is a proper, if you remember, an F pi minus 1 of the characteristic variety of n. And this is a map of a vector bundle. Proper, in this case, is equivalent to finite. It's not true in general. A proper map is not finite. But a proper map between two vector spaces is finite. Okay, so that's the definition of non-characteristic. Then what happens? Then first, the inverse image of n is coherent. So it means you have finite system of PDE on Y, which is non-characteristic for X. Then the induced system is a finite system. And so there is a notion that let's denote it for short by NY. Okay? And you have an isomorphism. The inverse image of the solution on X on N is isomorphic to the solution, here is X, Y, excuse me. Is isomorphic to the solution of X of, maybe it's not necessary, of df minus 1 n. That means the functor solutions commute to inverse image. That's Cauchy-Galevsky, revised by Kashiwara. And there is a similar result for direct images. So, yeah, there is a notion of good D module. We say that M is good if for any U relatively compact in X, so M is a coherent D module, then M restrict to U admits a good filtration. It means more or less that it is generated by a coherent O module. So we have the triangulated category dB good of dx, which is contained in dB coherent of dx. So it's coherent module with good filtration, not everywhere, but at least on each relatively compact open set. Okay. And then it's necessary for the proof. Where is that? So COM. So assume that F is proper. So we have M which is good on X. So right and left is not important. And assume F is proper on support of M. Okay. So when you integrate, you want compactness in the fibers. It's natural. Then what can we say? Then the direct image of M as a D module is good on Y. In particular, it is coherent. And again, it commutes with the RAM, or maybe I will take right module, but you can translate to left. Then the direct image of the DORAM on X of M is isomorphic to the DORAM on Y of the direct image of M. And there is a similar formula for the functor of solution, but they are shift. Idem for Seul. Almost idem with a shift. But Seul or de Rham are equivalent. Okay? So we shall need these things. Okay? And now I want to. Okay, so now I hope. Okay, so now I pass to holonomic D-module. So recall that M is holonomic so holonomic means the characteristic variety of M is Lagrangian. Okay. So recall that we have the functor Seul, which go from dB dx to dB cx. Then here I take holonomic D-module, and I say I will prove it. So it's a theorem that it goes in the category of constructible sheaves. So this theorem is due to Kashiwara again in 75, excuse me, 75. Okay? It's a very nice theorem, and I will give the proof. Of course, a sketch of proof if you want. So I take M dB all Cx. So first, so this is the functor of solution. Excuse me, yeah, it's opposite. Oh. So first, I say that Seul of M is weakly constructible. Weakly constructible means there exists a sheaf F is weakly constructible, means there exists a complex analytic stratification X equal union of X alpha, such that F restricted to each strata is locally constant. Okay. And it is a general theorem of sheaf theory. This is equivalent, for an object of derived category, I take all cohomology group. All cohomology group are locally constant on the strata. Okay. Maybe I give you an example in one dimension. X is open in C, and take OX, I don't know, Z dz minus 1/2 OX. Okay? So this is Seul of M when M is dx divided by dx Z dz minus 1/2. Okay? So what are the holomorphic solutions of this? So this is a local system on C, or let's say X equals C. On this on C minus 0 in degree 0, and there is H1 of this, which is supported by 0. This is a good example of a perverse shift, the simplest example of a perverse shift. Okay? So this first result follows from general result on shift theory. F belongs to dB W C C Cx if and only if the singular support of F is C Lagrangian. So this is a result which has nothing to do with PDE. It works on any field, in fact. So it's purely topological. Okay? So since we know that the macrosupport of sol of M is the characteristic variety of M, and this is by Cauchy-Kalevsky theorem, more or less, then this is Lagrangian, so the weak constructibility is obvious. So what means to be constructible? F a shift, assume it's already weakly constructible. We say that F is constructible if, moreover, the stalk HJFX is finite dimensional for any J, any X in X. Okay? There is a finite net condition, moreover. So let's prove. So let's prove the finiteness result. Okay. So we know that sol of M is weakly constructible. And let us prove that it is not weakly, but really constructible. Okay? So I choose X in X. On M, I can represent it by a bounded complex. This is keys to M. Let's denote by F for short. So the complex of solution is 0, then OX power N0, OX power NN, 0. So let's calculate the global section on BX. So this is the open ball at X of radius epsilon in some local cart, of course. Okay? So this is the complex, 0, then OX and 0 of B epsilon, OX and N B epsilon, 0. Because this is time, there is no cohomology of O. When I never use hypercohomology because I work in derived category, so R gamma is R gamma. Okay, and by the so let's call this F epsilon. So by the weak constructibility implies that the restriction morphism F epsilon to F epsilon prime for 0 smaller than epsilon prime to epsilon is a quasi-isomorphism. Because the shift is constructible, so the stalk at a point is the same as a small ball. Okay? Now, there is some functional analysis. This space, so I take F epsilon prime the restriction. Okay, so I need some functional analysis. I have F epsilon, which is a bounded complex of Fs spaces. Fs means Frechet Schwarz. On the map here is both a keys, but also the restriction, gamma of O B x epsilon to O B x epsilon prime. If epsilon prime is smaller than epsilon, this map is compact by a theorem of Montel. So it's a keys on it's compact at each step. Then the finiteness, the dimension of the cohomology of F epsilon is finite. And now it's another theorem of Ries from the beginning of 20th century. There are two Ries, I don't know which one, Marcel maybe. More or less, this theorem says that if you have a Banach space whose unit ball is compact, then the Banach space is finite dimensional. So it's more, this is a variation on this. Frédéric? I don't know. There are two Ries, I don't know. Anyway, they cannot complain any. So. Okay, so we have proved. So I think I have not given too many details. I don't have so much time. So we have proved that we go from dB all dx to dB c dx. We're up by the functor of solution. Okay. And a natural question will be, is this functor an equivalence of category? But it's known since long that it is not true, because if you take the two differential equations z2 dz minus z, so for m, so m means the quotient by this idea, and this, if you take z dz minus z2 dz minus 1, these two equations have the same solution. Same solve. Same complex of solution. Okay? Yeah. Cool. Okay. So I mean, M is D divided by this operator, and N equal D divided by the ideal generated by this operator. Then sol of M is isomorphic to sol of N. And it is well known that these two equations are not equivalent, these two modules are not isomorphic as D module, because this is very classical. This one has irregular singularity, is not Fuchsian, and this one is Fuchsian. Okay. So they cannot be isomorphic. Okay, so it's not an equivalence. So the question, but even to formulate the question was not so easy. So to formulate the question is as follows. The question is to find a full triangulated category that we will call regular holonomic, such that this is an equivalence of category. Okay. So of course it's inspired by what happens in dimension 1, where it is known that Fuchsian operators gives it's a Riemann-Hilbert problem in dimension 1, which is solved if it's correctly formulated. for Fuchsian operators. So the problem is to extend the definition of Fuchsian operator to D module, if you want. So this question was arised, I don't know how to write it, by Kashiwara again in 88, no, 78, and it appears in a book, in a paper by Ramis, when it says explicitly, Kashiwara asked this question. See? Kashiwara didn't write it, but it's the proof that he wrote it. And after, he proved it. So we have to define what is regular holonomic. And after, so what is the definition of regular holonomic? I lost it, of course. I know it, but okay, I forgot. I'm lost. So assume that let lambda be the characteristic variety of M. Okay. So we say that M is which is Lagrangian. M is regular holonomic if locally there exists a good filtration such that the graded M is O lambda. If you want, it's reduced. Okay. Or the ideal. Okay. So, okay. So I explained. Please? Yeah, so maybe it's not, well, yeah, so it's not a good definition. I forgot, it's lost in my notes. You have an idea for, maybe. So take U in M and take ideal satisfying IU equals 0, and you have that GRE I isomorphic to ideal defining lambda. Maybe it's more reasonable. You're right. In my notes, I think there is no mistake. But okay. So I explain what can be the inverse functor. Okay. So so let's call F equal sol of M. So the inverse functor, natural, will be natural to ask to this Rm F Ox. That's the most natural. So let's take an example, the simplest example. Take y given by x1 equals 0 in x equals Cn, okay? And M is H1 algebraic cohomology, okay? That is a meromorphic function or meromorphic function quotient by Ox, okay? So as a D module, it is generated by the ideal x1 d2 dn. Very simple. D holonomic, D module, regular holonomic. Okay? So if I calculate a sol of M, I will find the constant shift and y shifted by 1 or minus 1. I don't remember. Yeah. There is a shift. It's not the constant. Okay. 1 or minus 1. Okay, and if now I calculate Rm Cy Ox with a shift 1, so it was -1, I find H1 supported by, okay, and this is the holomorphic function in X minus Y. Oh, G star, it's not well written. Okay, it's a function with holomorphic function with essential. It's holomorphic functions with essential singularity on Y. And here it was meromorphic. Okay. So you see that the Riemann-Hilbert, what will be natural, gives infinite order differential operators. Okay, and we want finite order. That's the difficulty of D module. Because it's a mixture between analytic and algebraic, and that's the main difficulty. So, Schapira's proof, he introduced a functor, Tm, which goes from R constructible, because it's much easier to work with R constructible than with C constructible, sheaves to sheaves, to what? To D module. But after, with Schapira, we generalize this in another. We gave another approach that I will try to explain. How much time? I have not so much time. Okay, so it's a particular case of Tm f Ox will be rho minus 1 Rm f Ox subanalytic temperate. So I will explain very briefly, maybe, because it's in, and I will come back to this in my lecture Monday. So, but I think it's, of course, all ideas are contained in this functor theorem, but I think it's good to understand this temperate. So M now is a real analytic manifold, and I will change the topology. I define M as A, so it's a M and those with a Grothendieck topology. So here you have the open set M, but now the open set of M as A are the U relatively compact in M, which are subanalytic. So it's a class of open set or subset, which is very, very, very nice, and which has a lot of properties. On the covering, so this is a presite. On the covering, roughly speaking, are the finite covering. So it means a family UI is a covering of U, if and only if UI is contained in U, and there exists a finite set J finite such that the union of this Uj is U. Okay? So we just take finite covering. So with this new topology, we can define new sheaves, which are not sheaves for the usual topology. In particular, we can define C infinity temperate M subanalytic. So it means, on an open set U, it means that the d alpha phi of X for each alpha in a local card is bounded by some constant the distance of x to the complementary of u to some power. Okay? So it means it has polynomial growth at the boundary. Okay? So of course, for the usual topology, it's not local to have polynomial growth. But here we have only finite covering, and due to some result by Lozasevich, it works. So it's a sheaf. So this is a sheaf of temperate function, infinity function. And there is another sheaf you associate dB temperate of u, which means temperate distribution. It means distribution which can be extended to the whole space. So again, this is a sheaf. Okay, you know, temperate distribution means a distribution on a point set which can be extended to the whole space. Okay, so in general, it's not a sheaf for the usual topology. Okay, so I don't say more on the real side. And now, when I have a complex manifold, I look at, so X is complex, but of course, I don't write it, but it's, in particular, it's real. And I can put the subanalytic topology. And now I define O temperate X subanalytic as the Dolbeault complex R over the so X bar is a anti holomorphic manifold. So it's the same manifold that OX bar equal. So you take the Dolbeault complex, which is this one, is OX bar of, you have the choice, infinity temperate, or you can take dB temperate. It's a theorem, which is not so obvious, but they give the same result. Okay, so OT X SAU, but this is an object of the derived category, and it's not in degree 0 because we have only finite covering, but more or less intuitively it means holomorphic function with polynomial growth. Okay, and now, for example, if I take this example, then it's easy to see that H1 algebraic Y OX. So, yeah, I forgot to say that. So we have a morphism of site, okay, because here there are more open sets. So the inverse image of an open set here is an open set here, and the inverse image of a covering is a covering. Okay, so we have a morphism of site. Okay, so we can work. We have the as usual direct on inverse image. Okay, and then one can show that H1y is O minus 1 of R CY minus 1 OX with temperate growth. So it's natural. You take cohomology with temperate growth. Okay. Or more generally, even if Y is singular, this is still true. Okay. So the functor Thiom of Kashiwara, Thiom FOX, can be written as R rho minus 1 R FOX subanalytic temperate. That's the functor Thiom. So I want to give a sketch of proof of the theorem. So now we have the functor. Okay. And we want to prove that they are inverse one to each other. We have dB reg all dx sol dB cx on here we have rho minus 1 r om dot Ox subanalytic temperate. So the theorem says that these two functors are inverse one to each other. Sol is an equivalence with inverse given by this one. Okay. So I give a sketch of proof. Because there is a lemma which I like very much because it makes things very clear, very easy. So I give you the main lemma, and I will explain in the irregular case there is a similar lemma with a small modification, and I think it's a very nice lemma. So it's a formulated, maybe it's not a good formulation because we speak of a proper, maybe it's not well formulated, but everyone understands. So let Pxm be a statement for concerning complex manifold X and a regular holonomic module. So it means a regular holonomic module. I mean M dB reg all dx. Okay. Assume the following, or consider the following assertion. The statement is local. It means that if X is a union of open set, and if P, U, I, M is true for any I, then Pxm is true. The statement is local. The statement is triangulated. If you have a distinguished triangle, if P m prime and Pm are true, then Pm double prime is true. Or maybe, I don't know, it's equivalent or not. Yeah. Yeah, on, I forgot, where is the shift? Yeah, I forgot, but never mind. If P of X M is true, if and only if Px M shifted by anything is true. It's invariant by shift, by distinguished triangle. And until now, it's more or less obvious to check. And now it's more difficult to take a projective morphism. Then if Pxm is true, then this implies that Py of the direct image of M is true. If it's projective, it's proper, of course. So there is no proper assumption. And of course, we have to check on some examples. That's the last. Okay. So I will explain later. so I will say later, if M has regular normal form along a normal crossing divisor, so I will explain, then Pxm is true. Then, conclusion, then Pxm is true for any x, any m. And there is a similar, so I will explain what means normal crossing to be regular normal form. So assume, where is that? So assume that X is open in Cn with coordinate x1, xn. D is a divisor Z x1 equal xr equal 0. Then m is dx divided by I lambda. So take lambda equal lambda 1 lambda r in C, but we don't want positive integer. Okay, so there are no positive integer. Okay, and you take the ideal. So the ideal lambda is the left ideal generated by zi xi dxi minus lambda I for I between 1 and r, and dxj for j bigger than r. Okay. So that's the definition of regular normal form. Okay. So just a parenthesis for those interested in irregular holonomic D module. There is a similar lemma. Maybe I skip something. If P x m prime plus m second double prime is true, if and only implies, or if and only if Px m prime and Px m double prime is true. Okay, I forgot this one, but it's not necessary in the regular case, but in the irregular case it's necessary. So in the irregular case, I make a small parenthesis. Irregular case, you have the same lemma, but you replace regular normal form by normal form. On normal form, roughly speaking, means d of exponential phi, where phi is meromorphic. And this very important result is due essentially to Mochizuki, completed in the analytic case by Kedlaya, and preliminary result by Saba also. But mainly Mochizuki. Okay, but I don't speak of the irregular case here. But what means this lemma? It means that essentially you have two non-trivial things to do to prove that your statement is stable by direct image, and to check the statement on some very explicit case. So it's very deep, very useful result. I think it's more important than Riemann-Hilbert in some sense. Okay, so this lemma is due for the regular case. I think, I don't know, it has never been formulated like that, but it's known. But I don't know, we have to quote Deling, Kashiwara. And there are also many results in a paper, a very important paper by Kashiwara, Kawai. Okay. I'm unable to tell you exactly who has done what, but if you mix these three kind of paper, you find the lemma. So what remains, what we have to do to prove the theorem, but so in fact there is first I will prove something very useful also. Before to prove the theorem, I introduce the RAM temperate of M as omega x subanalytic temperate tensor M, and similarly sol temperate M is Rm d M OX subanalytic temperate. So there is a first theorem which says that if M is regular holonomic, then I don't know which one you want, maybe the RAM, let's say, then the RAM is equivalent, temperate, is isomorphic to the RAM non-temperate. Okay. And there is a first version of this result, which is due to Grothendieck in a letter to Atiyah, because Grothendieck, long ago, proves that the Durham cohomology of the complement of a hypersurface can be calculated using meromorphic functions. So it's exactly what it means. So when OX, when M equal OX, which is regular holonomic, we recover Grothendieck's theorem, which says that the Durham, of course, this applies. This is more general because as a corollary. So let's give a corollary. Maybe I put solution. Okay. So, for example, it shows that Rm for any R constructible F, Rm F of you put M where you want, Rm over dx, Rm F Ox is isomorphic to Rm, so it's like that, over dx, M Rm over F Ox temperate. Let's give an example to show you how deep the result is. Take an example. Take M real analytic on X a complexification. And take for F the dual on X of the constant shift on M. Then Rm rho minus 1 Rm F Ox T is the sheaf of Schwarz distribution on M. On Rm F Ox is the sheaf of Sato's hyperfunction. So you find that if M is regular holonomic, Rm M dB is isomorphic to Rm M B. And even in dimension 1, it's very difficult. So it's very deep. Okay. Okay. So what can we say for the proof? So the proof, I hope I have no time. Yeah? No, I have time. No, I hope that I had no time to give the proof. No, maybe so remember that we prove that, so we have to prove two things. Direct image, that the property is stable by proper direct image, projective direct image. On a particular case, we have to check the particular case of xi dxi minus lambda I dxj. So we have to check the theorem in both cases. So, yeah, no, something I can do in detail. First, I will prove that the functor yeah, okay. I will prove that the functor solution is fully faithful. So I will prove that sol is fully faithful. So let's write Rm of sol n sol m. So m and n are regular holonomic. So this is isomorphic to Rm sol n. So I follow my note. Maybe I don't write rho minus 1 for short. Rm m ox temperate. So there are a lot of small mistakes in my notes at this level. I should write rho minus 1 if you want. So it's isomorphic to Rm. So I put m here. M, so m d Rm sol of n oxt Oh, I forgot to say, it's too much. Yeah, I forgot. It's a little more, there is a corollary that I forgot. As a corollary, we can reconstruct M. We have M is isomorphic to rho minus 1 Rm sol of M oxt. But I skip, this is more or less a corollary from the RAM temperate of M is isomorphic to the RAM of M. But in fact, we need something stronger. We need OT, but I have not defined it. So I'm obliged to skip some part. So when I do that, it's Rm over d m n, which means fully faithful. Okay. Yeah, because I forgot to say something that I should have said from the beginning, that you can define OT tensor dm. Okay, I quit that. Okay, so full FS full follows. And there is another thing to be shown, is that the functor sol is essentially surjective. So it means that if f is constructible, then rho minus 1 r f ox subanalytic temperate is holonomic regular. Okay. And to prove that, one way, so it's in Kashiwara's paper, but one way, if you remember the lemma that I have erased, the main lemma, which says that we have to check property by, which are invariant by some properties, then there is a similar lemma for constructible sheaves. If you want to check a property on constructible sheaf, it's enough to check that it is invariant by sheaf, by distinguished triangle, by projective morphism, and finally, to check, you reduce to the case where F is a local system and the complement of a normal crossing divisor. Okay. So we reduce to this case and then we do it at n. Okay. Okay, so I don't say more. Maybe, no, I say something on the history. I'm not involved in the history, so I can give my point of view. So what is very important in the book by Deling in the 70s, we did Riemann-Hilbert for meromorphic connection. And after I explained you Kashiwara in 75 proves the constructibility. In 78 conjecture, and in 79 or 80, he gave a sketch of proof, but which is written down at École Polytechnique, a seminar of École Polytechnique, but it's written, it's not a talk, there are notes at Schwartz Polytechnique. And so there are important paper, Kashiwara Kawai mini tool in 81, and Kashiwara in 84. And there is another proof by Mepkut in 84. So everyone says it's Kashiwara Mepkut, but it's not my point of view. I don't think it's equivalent. But Mepkut gives a totally different proof, much easier, but not so interesting, because what is interesting, to my opinion, is that here we have the inverse functor. Okay? It's not a purely formal saying if this is true, and so. Here we have an explicit inverse functor. The proof is correct. I guess I've never read it, but I'm sure. Okay.